In this chapter, we will be using calculus as a tool in curve sketching. In this video, we'll sketch the function f of x equals 8x over x plus 1 squared.
All right, now the first function here that we're going to graph is 8x over x plus 1 squared. Okay, so number one, we're going to take a look at the domain, and actually, because it's a rational here, you can tell pretty quickly where the issue is going to be with the domain here. I cannot allow x to be equal to -1. Okay, because if I do, then the function becomes undefined. So that's it. That's the gap in our domain. So it's pretty straightforward. 2, the intercepts. Okay, well the first thing that I'm going to do here is I'm going to look for the y-intercept, basically because I'm lazy and I'm going to grab the low-hanging fruit first. Y-intercept is so easy to find. All I really have to do is evaluate the function at 0. Right? We just let x go to 0 because whenever x is equal to 0, that's going to be a point on the y-axis. And when you do that, you can see right away, because of that numerator, you're going to get 0 up there, but the denominator won't go to 0. The denominator is going to go to 1. 0 plus 1 is 1, squared is 1. So I'm going to get 0 here. Now, that's a pretty good indication that this graph is going to go through the origin, because when x is equal to 0, y is equal to 0. I'm still going to look for my x-intercepts here, because I could have more than just that one x-intercept, although I know already that there's going to be one. So in this case, you let the y-coordinate go to 0, and that's going to be 8 multiplied by x over x plus 1 squared. Now notice that I've got my fraction here equivalent to 0, but bear in mind that that won't happen when the denominator goes to 0. In fact, there is no value that I can plug into the denominator that'll make this thing equal to 0. So really, it's just about the numerator going to 0, and that's only going to happen when x is equal to 0. So really, the only point here that's significant in this discussion here is the origin. Okay, that's going to be both the only y-intercept and the only x-intercept. Okay, 3, let's take a quick look at symmetry. And to investigate the symmetry, basically what we do is we plug in -x and see what happens here. So if I plug in -x into the numerator and -x into the denominator, okay, well, a little something funky happens here in the denominator. When I multiply the numerators together, I'm going to get -8x, and that's totally okay. But down in the denominator, I run into a little bit of a weird situation here. I've got a -x plus 1. So what I'm going to do is I'm going to factor the negative out of this binomial. Okay, but I'm not going to factor it out of the square quite yet. I'm going to do this in steps. I'm going to factor it out of what's inside the brackets. Okay, I've still got the brackets where everything underneath there is being squared, and now I'm going to distribute the square to both the -1 and the x minus 1. But when I do that to the -1, that's a coefficient, -1 squared is simply going to become +1, and so it disappears. And so I'm left with, when I plug in a negative in here, -8x over x minus 1 squared, which isn't the negative of the original function. It's also not exactly equal to the original function. So what this means is this is neither odd nor even. So it doesn't have either one of those types of symmetry that we associate with either odd or even functions. So it's not symmetrical in any significant way that I would graph, or I could make use of while I was graphing here. Okay. Let's take a quick look at the asymptotes. Okay, now, I already know that this has got an essential discontinuity at x is equal to -1. So I'm suspecting there's a vertical asymptote at x equals -1. Now, what I should probably do is just investigate the behavior of the graph in and around -1 here. So I will take the limit as x approaches -1, let's say from the left. And I'm just going to go back up to my original function here. Let's take a quick look. If I let x approach -1 from the left, well, okay, the numerator really doesn't have any problems with that. If I just take a number really, really close to -1, but to the left of it, so like -1.1, -1.01, whatever, the numerator is going to become negative. When I do that to my denominator, a number that's slightly less than -1 plus 1 is going to be a number that's slightly less than 0. Just think about your number line there. Okay, here's 0, here's negative 1. If I take a number just slightly to the left of negative 1 and add 1 to it, I'm going to get a number that's still slightly negative. But when you square it, it becomes positive. So the numerator is negative, the denominator will become positive, which means this is going to go to negative infinity. In fact, anytime that I'm investigating the behavior around an asymptote, it's either going to go to positive or negative infinity. I know that. I should say a vertical asymptote. If I now take the limit as x approaches negative 1 from the right of f of x, basically the exact same argument can be made here. The numerator is still going to be negative, and because of that square, that denominator is still going to be positive, so I'm still going to get negative infinity. So as we get closer to negative 1, the graph is dropping down. Okay, it's dropping straight down. Now, does this graph have a horizontal asymptote? Well, we can figure that out just by comparing the degrees of the numerator and denominator. The numerator is linear, the denominator is quadratic. Yeah, it will. This is going to have a horizontal asymptote at y is equal to 0. That's what happens when the denominator's got a larger degree than the numerator. The denominator will grow faster than the numerator, causing the whole thing to collapse to 0. Good. Okay, now we're at the point where we can turn over to calculus and investigate what's going on here by using some of the calculus we know. So we're going to take the first derivative. Okay, so y primed is going to equal, now I'm going to use the quotient rule on this one. So the derivative of the numerator will be 8, and then the denominator was x plus 1 squared, minus the numerator multiplied by the derivative of the denominator, which will be 2 times x plus 1 to the 1, multiplied by 1, because the derivative of x plus 1, all over x plus 1 squared. Okay, well that's kind of busy. So what I'm going to do is I'm going to factor some stuff out here. I can take out an 8 out of the numerator. I can also take out an x plus 1. That is going to leave me with x plus 1 from this first term, minus, I took out the 8, I took out the x plus 1, so I'm left with a 2x there. X plus 1 to the 4th. We still see that? There we go. Move that up a little bit. Okay, now I can cancel out one of the x plus 1s there. Now that's so long as x doesn't equal negative 1, but I've already established that that's not true. So I can actually cancel that, and I'm okay. I've already covered my butt there. This is going to leave me with x plus 1 cubed down in the denominator. And up here I'm going to get, what is that? That's going to be negative x plus 1. And I'm probably going to factor the negative out of that and just make that negative 8 x minus 1 all over x plus 1 cubed. Okay, now I am curious as to the intervals of increasing and decreasing for this particular function right here. So what I'm going to do, and this is a tool that I've used way back when we first started exploring calculus here. I'm going to take a quick look at how this function behaves by splitting it into its individual functions. So I'm going to take a look at the number line here. Notice that this function here goes to 0. This x minus 1 is going to go to 0 at 1. So I'm going to put a 1 in there. And the denominator goes to 0 at negative 1. So in the numerator, I've got this negative 8. And as a function here, negative 8 is just going to be negative everywhere. It's going to take on negative values here, negative here, negative here, negative here, negative here, because it's always negative 8. There's no variable there for it to cause it to change values. It's always negative 8. No matter where you are on the number line, that function is always negative 8, so it's always negative. X minus 1, on the other hand, if you look at how it behaves all by itself, and by the way, that's what I'm doing. To figure out how the behavior of the whole function works along the number line, I'm going to break it into its individual pieces and look how each piece behaves. So x minus 1 takes on a value of 0 at positive 1. And then if we take in values to the right of positive 1, it's going to be positive. And if you plug in values less than 1 into here, it's going to be, it's going to be negative. It's going to be negative if you plug negative 1 into that. Negative 1 minus 1 is negative 2, and then negative for anything less than that. if you plug x plus 1 into this, and we will include the fact that it's cubed, x plus 1 is going to go to 0 at -1. Anything to the right of that, any value of x to the right of -1 will cause x plus 1 cubed to be positive. Anything to the left will cause it to be negative. Now, I have taken the individual pieces, okay, of this function and looked at how they behaved. So now I'm going to put it all together to create that function. Notice that these first two terms are in the numerator, so it's going to be a negative times a negative divided by a negative will be negative. So the whole function will take on a negative value if x is less than -1. At -1, it's going to be undefined because that 0 is in the denominator. Between those two values, between -1 and 1, I'm going to have a negative times a negative divided by a positive. That'll be a positive. Here, at -1, it'll be a negative times 0 divided by a positive. That's just going to be 0. And then for all values of x greater than 1, I'm going to have a negative divided by a positive times a positive. That's just going to be a negative. So what I see here is that f of the derivative, no, sorry, I should have put f primed of x there because I am looking at the derivative. The derivative is less than 0 on -infinity up to -1, and then from 0 out, sorry, not 0. Sorry, my mistake. It's 1. It's the interval from 1 out to infinity, which means that the function is decreasing on the interval -infinity to -1 union +1 out to infinity. But we include the +1, okay, because we include the endpoints where they exist. Now in this case we didn't include the -1 because the -1 didn't exist. It was an undefined there. My derivative, however, is positive on the interval -1 to 1, and then we include the 1, and that was it. So the function is actually only going to be increasing on that interval from -1 to 1, and I shouldn't have, I should not have included the 1 here because the 1 is making the function equal to 0, which means it's not, wow, totally forgot to put the 0 there. Okay, so anyway, so there you go. So now we've determined where the function is increasing and where it's decreasing. Now, really quickly, we can slide in here just before I get to the end of the page. I'm going to have to flip over in a second here, but we can do number 6 here real quick. We're looking for maximum and minimum points. Well, the only point that even looks like it qualifies as a possible maximum or minimum is when x is equal to 1. Okay? And when x is equal to 1, I can tell right now because it is the end point of an increasing sequence and the beginning point of a decreasing sequence here, or interval. I know that this is going to be a local max. Now it's also the only max here. It could be an absolute max. I'm going to have to take a quick look at the way that what else is happening on this graph, but that could be an absolute. Now I do want to figure out what the y coordinate is, so I'm going to go right back to the original function. If I let x go to 1 here, the numerator becomes 8, the denominator becomes 2 squared, or 4. So this is just going to be the point 1 comma 2. And that's where we're, whoops, sorry, can't see that. That's where we're going to get our local max. Fabulous. Okay, now, that was 6. Now we got a couple more things to do here. We got to take a look at concavity. So I'm just going to take a quick look here. My derivative was negative x minus 8, sorry, x minus 1. Negative 8 times x minus 1 over x plus 3 cubed. So let's take a look at, whoops, get this all together. Step 7. My first derivative was negative 8 multiplied by x minus 1 over x plus 1 cubed. And just because I don't trust my memory, I'm just going to double check that. Yep. So now, in order to investigate intervals of a concavity, I'm going to take the second derivative of that. And just like before, I'm going to use the quotient rule. So, the derivative of the numerator here will be simply negative 8 multiplied by x plus 1 cubed minus the numerator, negative 8 x minus 1, multiplied by the derivative of the denominator, which will be 3 x plus 1 squared, all over x plus 1 cubed squared, or x plus 1 to the 6th. Okay, now I will take out whatever's common here. And what I see is common here is a negative 8 and an x plus 1 squared. Okay, and when I do that, I am left with, out of my first term here, x plus 1 minus, now bear in mind that I've got the minus the negative, but I took out the negative 8, so that negative stays behind here. I took out an x minus 1 square, I took out an x plus 1 squared, so that one's gone. And so I'm left with 3 multiplied by x minus 1, all over x plus 1 to the 6th. Okay. We can cancel out a couple of those x plus 1s there, so this is going to be negative 8. This will be x plus 1 to the 4th in the denominator. And then in the numerator, what do we got here? Well, we're going to have an x and a negative 3x, so it's going to be negative 2x, a 1 plus a 3, so plus 4. Looks like, I'm just going to double check that, looks right. Up here, I am going to take out the negative 2. When I take that out, that'll be positive 16, x plus 2 over x plus 1 to the 4th. Now, once again, I'm going to take a quick look at the behavior of this function to see where it's positive or negative. So, again, I'm going to draw myself my little number line here because I'm going to take this thing apart and look at its pieces. The denominator goes to 0 at negative 1, and the numerator goes to 0 at, oh, sorry, I put that in the wrong spot. It's going to be negative 2 for the numerator, negative 1 for the denominator. Okay. Oh, shoot. No, I was anticipating, I'm sorry, that little pause there was because I know what this is supposed to look like, and I can almost hear people saying, wait a minute, you screwed that up. And yeah, I did. When I factored out that negative, that should have become a positive. Sorry, I knew that that negative 1 was supposed to be the one on the farther right there, so it should have been negative 1 and positive 2. Those are those two spots that I need to consider for the way this function behaves here. So I've got this 16 here, this function 16, and it is positive everywhere because it's just the number 16. X minus 2 is going to be 0 at 2, positive to the right, and negative for every value, every interval to the left. X plus 1 to the 4 is going to be 0 at negative 1, and then because of the 4th power there, it'll be positive everywhere else. And so now when we put that second derivative together, in this interval over here to the left of negative 1, I'm going to have a positive times a negative divided by a positive. That'll be negative. Positive at negative 1, it's a positive times a negative divided by 0. That's undefined. Here it's a positive times a negative divided by a positive. That's going to be negative. Here, that 0 is in the numerator, so it's going to be 0, and then it's positive over here. So what I'm seeing here is that my second derivative is positive, okay, on the interval from 2 out to infinity, which means the graph here is going to be concave up on the interval from 2 out to infinity, including the 2. Okay, so the second derivative is positive on the open interval. It's concave up on the closed interval. The second derivative is negative, okay, on the interval from negative infinity to negative 1, okay, not including the 1 because that's where it's undefined, union, and then it's going to be negative 1 out to 2, which means this is going to be concave down on the interval, negative infinity to negative 1, again, not including the negative 1 because that's an asymptote, union the interval from negative 1 to 2, and including 2. So right away, once we take a look at this, we can actually go to step 8, and we can identify our points of inflection. And in fact, I've really only got one candidate for this, because I've only got one point here where the graph here the function here, the second derivative goes to 0. The only other place that might have been a concern is where it was undefined, but we know right from the beginning that was an asymptote here. So the only number here that could be an issue here is going to be where x is equal to 2. And actually that does qualify as a point of inflection here because it changes from concave down to concave up. So good, point of inflection. All I'm missing now is the y coordinate. So let's go back to our original function. If you plug 2 into your original, 8 times 2 is 16. 2 plus 1 is 3. Squared is 9. So it's going to be 16 over 9. 16 over 9. So a little under 2. Okay, so those are our 8 pieces. Now let's put this all together. Okay, so here's my graph. I know that I've got an x-intercept right there. In fact, my x and my y-intercept are right there. I know that this graph had a vertical asymptote at -1. I know that it has a horizontal asymptote at y is equal to 0. I knew that it wasn't symmetric here. Now, in terms of the first derivative, and I got to go just take a quick look back here. The first derivative, what did it do here? It was negative until -1, then it became positive, 0, 1, negative. So when I take a look at my graph here, here's my -1, here's my 1. I'm going to just take a quick look. I'm going to draw a line up here to identify what's going on with my first derivative. There's a break here and a break here. It was negative, positive, and negative. Did I say that right? Yeah, negative, positive, negative. Good. Down here, I'm going to identify the interval where my concavity changed. And my concavity changed at -1, which I totally expected because that was my asymptote. And then it was out here at 2. Okay? And it was, what did I say here? It was concave down here, concave down here, and then concave up here. And that actually leads us to our other points that were significant. We had a maximum point at 1, 2. Okay, so if we put that right there, there's 1, 2 is going to be right there. And I've got a point of inflection at 2, 16 over 9, which is going to be a little bit less than 2. Okay, so what does this now look like? All the pieces are there, we just got to put it together. Well, in this section right here, I've got an asymptote here, vertical asymptote, horizontal asymptote here. The graph is decreasing and concave down. So decreasing and concave down. It does not cross the x-axis, and we know when we took the limit that it goes down to infinity. So the function's got to look something like that. Okay, it's got to look something like that. Now, on the right-hand side, it's increasing and concave down, and we know that it approached the vertical asymptote going down, so this has got to be coming up like this. It's got to go through our x-intercept right there. It comes up, it hits a maximum, okay, so the tangent goes horizontal right there, hits a maximum. At 1, it starts to go down, starts to decrease. It's still concave up though, still concave up until it gets to this point. It continues to decrease after that, changes to concave up, and approaches the horizontal asymptote. And so there it is. That's roughly what our graph should look like.